Our planet, as magnificent as it is just one planet circling an ordinary star in a rural section of our galaxy. The Milky Way isn't just a static collection of stars, however, but a roiling, dynamic place. Stars are born in the collapse of gigantic clouds of dust and debris. They keep themselves alive by consuming the primordial hydrogen of the universe. They use nuclear processes to create the heavier elements, including the carbon that makes up much of your body. Eventually, stars run out of fuel and die, returning their heavy elements to the interstellar clouds from which new stars and planets are made. In death, they leave behind a strange menagerie of objects, including white dwarfs, pulsars, and even black holes. In recent decades, astronomers discovered that just as the inner planets are actually a small part of the solar system, the mighty pinwheel of the Milky Way is just a small part of the galaxy. In fact, the spiral arms of the Milky Way are enclosed in a mysterious substance known as dark matter. Puzzling out the nature of dark matter remains a major research project today. Interested yet? Because that's what we're going to talk about. We're going to talk about the Milky Way, our own galaxy, our own hometown in the universe. Last time in our Beyond Earth series, we talked about our very own neighborhood, and that is the solar system, but this time we will talk about the Milky Way. So welcome to a new episode from our Beyond Earth series. This is your host, Danny, and this is English Plus Podcast. So let's start our journey in the Milky Way by talking about the Sun, the star next door. Every day on Earth begins when one representative star of the Milky Way galaxy, a very ordinary star, pokes its nose above the eastern horizon. The Sun plays such a central role in life on Earth that it is easy for us to forget that it is, after all, just one more star in a galaxy full of them. Everyday experience can lead you to one of the great scientific questions that occupied astronomers when they began thinking seriously about the sun. Stand outside on a summer day and feel its warmth on your face. Energy is coming to you from the sun. This energy has to come from some source inside the sun, but what? It wasn't until the early 1930s that the young German-American physicist Hans Bethe showed that the energy source of stars was the process of nuclear fusion. And this means that every star must sooner or later run out of energy. Stars are not forever, but are born and die like everything else. So what is this power at the core of the sun? The Sun and the solar system formed from the gravitational collapse of an interstellar dust cloud, with more than 99% of that dust cloud being incorporated into the Sun. One of the basic rules of nature is that as objects contract, they heat up. So when the great gas cloud contracted, it got warmer. The particles and atoms that made up the cloud moved faster and faster, and the collisions between them became more and more violent. Eventually, they became so violent that electrons started to be torn loose from their atoms. The material in the sun became what physicists call a plasma, a collection of negatively charged electrons and positively charged nuclei moving around independently of each other. And now let's talk a little bit about the sun's structure. For 4.5 billion years, the sun has been burning hydrogen at the rate of more than 400 million tons per second. And it will continue to do so for another 5.5 billion years. The core of the sun, where it is hot enough for nuclear reactions to occur, extends outward about a quarter of the way to the surface. Moving outward from the core to about 70% of the distance to the surface, we encounter what is called the radiative zone. In this region, the fast-moving particles experience a series of collisions. Beyond that, the density of matter becomes too low for these kinds of collisions to impede the energy flow, and the sun actually boils, just like water on the stove. This convective zone extends almost all the way to the surface. Looking at the sun from the outside is a little like looking down into murky water. We can see only about 160 kilometers or about 100 miles deep into the sun through the thin outer layer called the photosphere. Above the photosphere are tenuous layers of atmosphere such as the corona, which is visible during the eclipses. And there's the heliosphere, which actually extend out past the orbit of Pluto. And because the sun is not solid, different parts of it rotate at different speeds. This difference, together with a constantly churning convection beneath the photosphere, causes the magnetic field of the sun to be constantly twisted, distorted, and pulled around, giving rise to phenomena like sunspots and solar flares. Sunspots go through an 11-year cycle in which the number of observed spots increases and drops. The solar cycle, and particularly solar flares, can have an effect on things like satellite operations and radio transmissions on Earth. So that is in a nutshell about the sun, this star that we have next door, which is the source of life as we know it here on Earth. But that was just the beginning of our journey in the Milky Way. Of course, we started from something we think we know, but trust me, we still don't know anything about. Or at least let's not say anything, but we still have a lot to learn about our own sun, this star next door. But for our journey today in Beyond Earth series, we're not gonna stop here. We're gonna go further, and next we're gonna talk about exoplanets. So that's coming next. Don't go anywhere. I'll be right back. The idea that there are planetary systems circling other stars is an old one. Only in the last few decades, though, has the search for extrasolar planets or exoplanets become a major feature of galactic astronomy. The reason for the delay is simple. The technology was not yet up to the task. Planets shine by reflected light and are thus much dimmer than stars. Furthermore, they are located close to stars, so whatever light they send out is swamped by light from their parent star. One astronomer likened the problem of seeing an exoplanet directly to detecting a birthday candle next to a searchlight in Boston by using a telescope in Washington, D.C. Consequently, the discovery of exoplanet had to wait for new kinds of detection techniques. So let's talk about the very first detection. The first successful technique for detection of exoplanets is known as radial velocity measurement. To see how it works, imagine that you are an observer looking at our own solar system from a distance of many light years. We are accustomed to thinking of the sun as being stationary while planets circle in their orbits. But in fact, the sun moves around a bit in response to the planet's gravitational pull too. For example, if Jupiter lay between you and the sun when you were making your observation, the sun would be pulled slightly in your direction. Later, when Jupiter revolved behind the sun would be pulled slightly away from you. Over a 10-year period then, you would see the sun moving toward you for a while, then away from you. This motion can be detected by observing the Doppler shift in the light the sun emits. Bluer as it moves toward you, redder as it moves away. So, although you couldn't see Jupiter directly, you would know that it is there because of its effect on the sun. The first detection of an exoplanet in 1992 involved a rare case in which the planet must have formed after its parent star became a supernova. This was followed in 1995, however, by the discovery of a planet circling a more conventional star in the constellation Pegasus, and with this, ushering in the modern era of exoplanet detection. At first, the discoveries came in slowly at the rate of a few a year, but as the technique improved, the pace picked up. We now know of several thousand possible planetary systems around other stars, and astronomers predict that there will turn out to be billions of planets in our own galaxy. And talking about that, we need to talk about the Kepler mission. Now, Kepler is a spacecraft weighing it at a little over a ton. It is equipped to provide continuous monitoring of the brightness of more than 150,000 stars in our immediate galactic neighborhood. Because a satellite in low Earth orbit can have up to half the sky blocked by Earth's disk, and because Kepler needs to watch the sky continuously, the spacecraft is actually maintained in an orbit around the Sun, not the Earth. You can think of it as trailing along behind Earth like a miniature planet. The basic planet hunting technique used by Kepler is simple to describe, but requires sophisticated equipment to make it work. The central idea is that if a planet passes in front of a star, the brightness of that star will drop while the planet is making its transit, then pick up again as the planet moves past in its orbit. Of course, this so-called transit method of detection works only if the orbit of the planet takes it directly between the star and the observer. For example, if someone were observing our solar system, Jupiter could be detected by the transit method if the observer were located on the same plane as the planetary orbits, but not if he or she was above or below it. This means that only a tiny fraction of planetary systems can be detected by transit techniques. On the other hand, Kepler scientists are quick to point out that the transit method has one important advantage over the older radial velocity technique. In order for a planet to influence a star enough to produce a detectable Doppler shift, the planet has to exert a large gravitational attraction on the star. This means that the radial velocity method is most likely to detect large planets orbiting close to their stars, and these are the so-called hot Jupiters. Indeed, most of the planets detected before the Kepler launch were of this type. The transit method, by contrast, detects any planet that affects its star's brightness regardless of its size or distance from the star. In fact, one of Kepler's most important results is the realization that the hot Jupiters are not all that common. They were just the first exoplanets to be seen. This came as a great relief to scientists who study planet formation because theory tells us that large planets should form far from their stars. So while the detection of exoplanets started slow, it really picked up speed until we reached a place where we have a treasure trove of exoplanets. By early 2013, the Kepler team had identified more than 3,500 possible exoplanets. Astronomers refer to these objects initially as candidates. This is not a case of excessive caution, but simply recognition of the fact that events other than planetary transits can cause a star's brightness to flicker. A large collection of sunspots could do this, for example, as could an eclipsing binary star so close to the line of sight that the spacecraft can't tell that it is a separate object. A minimum requirement then is that the transit repeat at the regular intervals appropriate for a planet in orbit. In fact, Kepler scientists describe two hurdles that a candidate must overcome before it is granted the rank of planet: confirmation and validation. Confirmation requires that enough data be gathered to determine the object's mass, usually by having ground-based telescopes measure the star's radial velocities after Kepler has identified a likely system. In some cases, monitoring the transits of several planets in a system allows scientists to work out the complex dynamics of motion and get the masses that way. Validation is the process of going through the data carefully and eliminating all the false positives that could fool you into thinking you had found a planetary system. Now, unfortunately, in May 2013, the Kepler spacecraft lost functioning in the second of its 4 gyroscope-like wheels, a loss that deprived engineers of the ability to point the spacecraft precisely. Although it can still carry out some studies, the spacecraft which completed its prime mission in 2012 will be of limited use in the future. The real holy grail of planetary science, an Earth-like planet that could support life or perhaps already does, will be found by spacecraft following the trail that Kepler blazed. Over the past 50 years, scientists have discovered life in unexpected places right here on Earth. Newly discovered forms of life called extremophiles thrive in conditions such as highly acidic and highly salty environs that would have killed ordinary bacteria. The first ones were discovered in the 1960s in the hot springs of Yellowstone National Park, with water temperatures well above the boiling point. These discoveries have had a profound effect on science, suggesting new theories on how life developed here on Earth and where life can be found on other planets. So, this is what I wanted to tell you about exoplanets. I'm sure you heard of exoplanets before, but I hope that after I talked about them this way, you know exactly what we mean by them and the methods we have to discover these exoplanets. Now, of course, nothing is for certain, but we all have theories and we're just trying. And by doing this, we will come to the very next topic in today's episode, and that has to do with SETI and the question, are we really alone? That's coming next. Don't go anywhere. I'll be right back. The 1961 conference at the National Radio Astronomy Observatory in Greenbank, West Virginia, gathered 11 scientists to talk about the possibility of communicating with extraterrestrials. The conferees eventually summarized their estimates of the number of extraterrestrial civilization in a compact notation that has come to be called the Drake equation, after Cornell astronomer Frank Drake, one of the organizers of the conference. So what is this Drake equation? The equation estimates that the number of extraterrestrial civilization trying to communicate with us, and here of course I'm not gonna tell you about the equation because honestly I don't really understand it myself, it's kind of complicated, but it takes into account the rate at which suitable new stars are forming, the probability that the star will have planets, the number of planets capable of supporting life, the probability that those planets will actually develop life, the probability that life will develop intelligence, and also the probability that intelligent life will develop a technology capable of interstellar communication. And finally, the length of time that communication once started will continue. So all these factors taken in and put in one equation, which is called the Drake equation, is a useful way to organize our knowledge and our ignorance, of course, and it is the basis for search for extraterrestrial intelligence, and that is what we call SETI. S-E-T-I, the search for extraterrestrial intelligence. You might have thought that we were talking about a specific planet. Not really. That is what SETI stands for, Search for Extraterrestrial Intelligence. Now, the Greenback attendees, and based on the Drake equation, came up with the most probable estimate for the number of civilizations possible that could possibly communicate with us of around 1 million civilizations. The idea of a vast, intercommunicating galactic club made up of thousands of intelligent species entered the public consciousness, fueling countless science fiction scenarios. But although the Drake equation started those possibilities and started those ideas in science fiction and everything, but the main question remains, where is everybody? In the beginning, there was modest federal support for SETI programs, but when the searches failed to turn up anything interesting, that source of funding waned. Today, the SETI program is being carried forward using private funding. When you think about the problems involved in the search, you can see why it is taking so long. There are billions of stars out there, and a good proportion of them probably have planetary systems. With each star, you have to follow a slow process. You don't know what frequency the aliens might be using for their broadcasts, so you slowly move, pausing long enough at each position to see if something interesting is coming through. Today's SETI searches make use of modern fast electronics to monitor thousands of stars and thousands of frequencies at once as they sort through a mountain of data. The point about SETI, though, is that no matter how the search turns out, it's worth doing. Are there ETs out there? That's fantastic. Are we alone in the galaxy? Even more fantastic. There aren't many other kinds of scientific activities with this kind of payoff. But until now, we still have this big question that is, where is everybody? Now, yeah, we have estimated according to the Drake equation that there might be over 1 million possible civilizations trying to communicate with us, but where are they? As far as we know, there's nobody. Or nobody tried to contact us, or at least maybe they tried to contact us, but we couldn't pick up the signal, or we didn't understand that this was a signal. Maybe they are not as intelligent as we are, or we are not as intelligent as they are, or maybe there are some secrets. Maybe there were some interceptions, but they're being kept in the dark until we figure out what to do with them. Now, of course, I'm not talking about conspiracy theories here. I really hate conspiracy theories. But the point is that it is possible, and from a governmental point of view, you may not want to reveal everything no matter how exciting it might be until you figure out what it means. But anyway, as far as we know, we still haven't received a single alien message that we can understand at least. And this is all about SETI, Search for Extraterrestrial Intelligence. So we're still talking about the Milky Way, we're still talking about galaxy. What are we going to talk about next? Well, actually, we're going to talk about stars in old age. Well, we know that our own star is kind of middle age, right? But what happens to stars in old age? That's what we're going to talk about next, so don't go anywhere. I'll be right back. All stars begin life the same way our sun did, as a condensing cloud of interstellar dust. From then on, the star is using various means to ward off the eternal inward pull of gravity. we discussed the first of these strategies in the birth of our own sun. It is the initiation of nuclear fusion reactions in the core which sets up an outward pressure to stop the cloud from collapsing. Almost every star you see is in its hydrogen burning phase. Astronomers call them main sequence stars. Our sun has been in this phase for roughly 4.5 billion years. Obviously, hydrogen burning can't go on forever. Sooner or later, the hydrogen fuel in the star's core will run out, and the star will have to develop a new way of countering gravity. How long that takes depends on how big the star is. There are two competing effects here. On the one hand, bigger stars have more fuel to start with. On the other hand, bigger stars also generate a stronger gravitational force and have to burn fuel faster to overcome it. It turns out that the second effect wins, and the bigger a star is, the shorter the time it can spend burning hydrogen. If you imagine the Milky Way galaxy being a year old, for example, a star like the Sun might have fuel enough for 10 months or so, while very large stars might last as little as half an hour. So what will happen to a typical star like our own Sun when the hydrogen in its core runs out? As the nuclear fires start to fade, the pressure that has held off the forces of gravity for billions of years will grow weaker. Gravity will take over again, but then the star's interior will heat up again as it gets denser. Eventually, the temperature of the core will increase to the point where a new kind of nuclear fusion can take place, with 3 helium nuclei coming together to produce a carbon nucleus. This sort of sequence, in which the ashes of one nuclear fire becomes the fuel for the next, is one of the major features of energy generation in aging stars. In the end, for stars up to 6 times as massive as the Sun, the renewed fusion reactions will increase the star's energy output as well as cause its atmosphere to expand. The edge of our Sun, for example, will eventually extend outside the current orbit of Earth. Because the star's energy is being sent out through a much larger surface, the color of that surface changes from white hot, as in the Sun today, to a cooler red. A star like this is called a red giant. Stars 9 or 10 times more massive than the Sun have enough mass to push the temperature high enough to repeat the process beyond the helium burning stage. When the collapse starts again, the carbon nuclei in the innermost core combine with others to produce heavier elements. This fusion process can continue through the periodic table, with the star developing an onion-like shell structure as successively heavier elements are created by each collapse. Iron is the end of the line. You can't get energy from iron by splitting it or by adding to it. It just builds up in the core of the star like ashes in the grate of a wood stove, setting the stage for one of the most spectacular events in the universe, which is called a supernova. As iron accumulates in the heart of the star, nuclear forces cannot keep it from collapsing under the influence of its own gravity. When the mass of the iron core gets to about 40% more than the mass of the Sun, gravity can force electrons and protons together to produce neutrons. As each electron disappears, the ability of the remaining electrons to counteract gravity decreases, and in a very short time, the core turns into a mass of neutrons that collapses catastrophically. As the core implodes, the remnants of the onion-like envelope of heavy elements that the nuclear reactions have built speed outward in a spectacular explosion. Our home galaxy started off billions of years ago as a cloud made up primarily of hydrogen and helium. As large, short-lived stars were born and became supernovae, heavier elements began to appear. One way to think about the Milky Way then is to picture it as a giant machine constantly taking in primordial hydrogen and churning out the rest of the chemical elements. Our own solar system formed late in the history of the Milky Way, incorporating into its planets and even its life forms the heavy elements made by long-dead stars. So what about the properties of a neutron star? Inside the exploding supernova, the collapsing core is simply a mass of neutrons. Because neutrons have no electrical charge and therefore do not repel each other, there is no radiative force to counter the force of gravity in the heart of the star, and the core goes into free fall. This fall stops only when the neutrons are packed so tightly that the core cannot get any smaller. This is known as a neutron star. Because the mass of a neutron star is so concentrated, the force of gravity at the surface is huge. The collapse also produces an extremely strong magnetic field. In addition, the rate of rotation of the core increases during the collapse, just as an ice skater's rate of spin increases when she pulls in her arms. Some neutron stars rotate at nearly 1,000 times a second. It can be that fast. And as the neutron star rotates, its intense magnetic field is swept around in a circle, creating electromagnetic waves. The star emits a beam of radio waves that travels outward along the direction of the star's magnetic axis. Like a lighthouse beam sweeping around in a circle, the rotating neutron star sends out a radio beam that sweeps through space. If you have a radio receiver in the path of the beam from a rotating neutron star, you will see a burst of radio waves when the magnetic axis points in our direction, followed by a period of no signal, and then another burst, and so on. In 1967, scientists at a radio telescope in England first observed these sorts of regular pulses, and the word pulsar was coined for these objects. Since that first discovery, a couple thousand pulsars have been discovered in the Milky Way. Amazing, isn't it? I mean, you might not be that interested in astronomy, the universe, whatever, but to learn about these things, to learn about the great possibilities out there and what is really happening, and again, I'm telling you that we know very little of our own planet before talking about the solar system, the Milky Way, or even the universe, which we will definitely talk about in our Beyond Earth series. Even some of these are theories, or even some of these are our own interpretations of what's happening around us. Maybe they're not exactly like that. Maybe in the years to come, we will figure out that we were wrong in some of our own interpretations, and we will figure out some new ways to really discover life somewhere else in our galaxy or even in the universe. But until this happens, I will always find this information or any information about the universe so mind-blowing that I really have to share it with you. And that's why I created Beyond Earth series. And remember, today's episode, we were talking about the Milky Way, and we're not done yet. We still have a couple of things to talk about. We're going to talk about black holes and dark matter. That's coming next. Don't go anywhere. I'll be right back. There is probably no object in the sky that has been taken up so wholeheartedly in modern fiction and common usage as the black hole. The short definition of a black hole is that it is an object so massive and so compact that nothing, even light itself, can escape the gravitational pull at its surface. We expect that stars that begin life with 30 times the mass of the sun and go through the supernova process will wind up as black holes. The boundary in space that separates the interior of the black hole from the rest of the universe is called the event horizon, and it marks a point of no return. A distant observer watching an object falling into a black hole would see time on the object slow down and stop at the event horizon. An observer on the falling object, however, would see no change in a clock that was traveling with him. And you can see why black hole is actually the fuel of a lot of science fiction. I mean, this time problem is enough to fuel a lot of science fiction stories. So, we talked about the black holes, what they are. What about finding black holes? How do we find black holes? Astronomers think it likely that all or almost all galaxies have black holes at their centers. But how do you find something you can't see? For one thing, black holes exert a gravitational force, and that can be used to find them. Another way to spot black holes is through radiation from their vicinity. Matter falling into a black hole tends to bunch up, forming what is called an accretion disk. Collisions in the disk heat it up, which emits energetic radiation. The star Cygnus X, which is a strong X-ray source, is one of our best candidates for a stellar black hole. We can have no direct knowledge of the interior of a black hole for the simple reason that there is no way for information to get out. Our mathematical models predict that there may be a singularity there, a place where the curvature of space-time becomes infinite, and the known laws of physics would break down at a singularity. So who knows? Maybe we will figure it out one day, and maybe we will never figure it out, because until now we have theories about black holes, but we don't know exactly what's in there, because obviously not even light can escape the gravitational pull of a black hole. And black holes, of course, are not the only mysterious phenomena in the universe. We also have dark matter, the invisible galactic halo. One of the most startling discoveries of the late 20th century was that ordinary matter, the stuff we are made of, is just a small part of our universe. Most of the universe consists of something we've never seen or detected. To understand how this discovery was made, we'll have to think about how galaxies rotate. Our galaxy, for example, rotates like a giant pinwheel over periods of hundreds of millions of years, with our sun making a grand circuit every 220 million years or so. One way that astronomers study the structure of galaxies is to look at the details of galactic rotation. The main tool in this study is something called a rotation curve, in which astronomers plot how fast a star is moving as a function of how far away from the galactic circle it lies. Stars in the densely populated galactic center, locked together by gravity, rotate together. This rotation is similar to what you would see on a merry-go-round. If you are standing near the inside of the platform, you will be moving fairly slowly, but as you move outward to the periphery, you will be whirling around faster and faster. The rotation curve for this situation shows the speed increasing steadily as you get farther away from the center. In the jargon of astronomers, this kind of rotation is called wheel flow, since it is characteristic of any solid rotating object. But as we move outside the galactic core, we find that all the stars are moving at the same speed, regardless of how far they are from the center. This is a situation similar to what you see at a track meet where runners on an oval track have to stay in their lanes because the runners in the outer lanes have to travel farther. They usually start farther ahead than the runner in the inside lane. If this weren't done, the runners in the outside lanes would gradually fall back. The same thing holds for the stars in a galaxy. The farther out they are, the more they fall back compared to stars closer to the center. You can see this situation manifested in the curved spiral arms of many galaxies. So what happens to the galactic rotation curve when we move still farther out? And here, let's have this little thought experiment. Imagine getting so far away from the galaxy that the whole pinwheel shrinks down to a single faint point of light in the distance. Even out there, the galaxy will exert a small gravitational force on you, so you will still be orbiting that distant point. You would expect, though, to be moving very slowly like the outer planets circling the Sun in our solar system, just as Neptune moves much more slowly in its orbit than Earth. Once you are this far away from a galaxy, you would expect the speed of any material out there to get slower the farther away it is. This is called Kepler rotation, after the famous astronomer Johannes Kepler, who discovered the law for planets in the solar system, which is represented by the downward trending tail of the rotation curve. Yet even here, the stars move at the same rate as inside the galaxy. It was the failure to see this downward trending Kepler flow that led scientists to the discovery of dark matter. As astronomers traced the rotation curve into the far outskirts of other galaxies, they didn't see the downturn they expected. In the early 1970s, Vera Rubin, who was then a young astronomer at the Carnegie Institution of Washington, began using advanced imaging instruments to measure the rotation curves of galaxies. Starting with the nearby Andromeda galaxy, she was amazed to observe that the curve stayed flat out to the limits of what she could measure. The stars kept moving at the same speed no matter how far they were from the galactic center. Galaxy after galaxy gave the same result. In 1978, astronomers realized that their expectations about the rotation of galaxies were simply wrong. They determined that the only way to explain the observed rotation of the galaxies was to say that the visible part of a galaxy, the stars and the dust cloud we've been exploring, is enclosed in a giant sphere of matter that we cannot see, but whose effects we can observe. The term dark matter was quickly applied to this new material, and that was the story of the discovery of dark matter. But what are the properties of dark matter? Now, I'm not saying that we know that for sure, but at least theoretically. Whatever dark matter is, it does not emit or absorb light or other electromagnetic radiation, nor does it have any other kind of interaction with ordinary matter except for gravity. The usual tools of the astronomer, optical and radio telescopes, for example, are useless where dark matter is concerned. This means that while we can detect dark matter by observing its gravitational effect on luminous matter, for example, the effect it has on the rotation curve, we cannot see it directly. Once the idea of dark matter surfaced, evidence for its existence in other venues showed up quickly. For example, there are stellar clusters in which individual stars are moving too fast to be held together by the gravitational attraction of the other stars. In these cases, some extra gravitational oomph is needed, and that, of course, is what dark matter supplies. Today, astronomers believe that dark matter makes up 23% of the mass of the universe, compared to a bit less than 5% for luminous matter like stars. The rest is another, even more elusive category called dark energy that we will talk about in the next episode. But now let's stick to dark matter. Calculations show that for a galaxy like the Milky Way, more than 90% of the galaxy's total mass has to be in the same new and unexpected form. So if there is so much of this stuff around, what is it? Theorists have not been slow in producing hypothetical answers to this question. The most popular candidates for the missing matter are as yet undetected objects known as weakly interacting massive particles, or WIMPs for short. Another class of theories involves something called supersymmetry. These theories predict that they are so-called supersymmetric partners for all of the known elementary particles that will presumably be seen in accelerator experiments. The theories are interesting, but of course, the only way we'll know for certain what dark matter is made of is to have someone identify the stuff in a laboratory. Many processes, particularly collisions with cosmic rays, can jostle atoms and mask the very faint dark matter signal. For this reason, dark matter searches tend to be located deep underground in mines or tunnels where the overlying rock provides a shield against this sort of interference. A typical dark matter search experiment is located in an abandoned iron mine in northern Minnesota. The mine in the town of Sudan is in the middle of the famous Masabi Range that supplied much of the iron that built early 20th century America. The mine is now a state park. In a chamber more than 600 meters or 2,000 feet beneath the surface, a stack of ultra-pure germanium and silicon wafers is cooled to within a fraction of a degree of absolute zero. Scientists hope that a few of the particles in the dark matter wind sweeping through the mine will interact with atoms in the stacks, producing vibrations that can be detected by instruments on the crystalline surface. To date, no generally accepted dark matter discovery has been made, although some groups have tantalizing results. This means we are in a position of knowing that 90% of our galaxy is made of some new material, but we don't know exactly what it is. So my friends, that was what I wanted to share with you about the black hole and dark matter. Now, of course, in today's episode, we talked about the Milky Way, our own galaxy, and our discussion of the dark matter will be the end of today's episode. Next time, we're going to talk about the universe. So we're going even bigger. We're reaching even farther into the universe before we continue our series with a series of interesting questions that are still mysteries of the universe. Or maybe we kind of solved a couple of them, but definitely not all. I hope you enjoyed today's episode and you learned some new things. Don't forget that you can find the transcript of this episode on my website, EnglishPlusPodcast.com. And while you're there, you can explore the many learning opportunities you have on the website. I would like to thank you very much for listening to another episode from English Plus Podcast and another episode from our series, Beyond Earth. Don't forget to learn a new thing every day with English Plus Podcast. And that'll be everything for today. This is your host, Danny. Thank you very much for listening. I will see you next time.